Excellent. All right. Good afternoon, lads and ladies. Today, we are going to talk about application problems, real-world problems involving exponential functions and logarithms. This is our last topic before exam 3, which you may recall from our last class, had to be pushed from this week to next week due to the holiday this Wednesday. So without further ado, let's get in here. Yes. Yes, indeed, next Monday. So a week from today. It might be the computer processing the video from my last class. My last class did just end. So today, I'm going to talk about application problems. And we can do some review, whatever you guys want to do after I introduce the application stuff. Remember, exam 3 is next Monday, 1 week from today. Which is, what's the date there? The 16th. During normal class time. Okay, so I got a few questions there. Yeah, audio hopefully should be improving. I think it's maybe just because I'm buffering a video from last time. What was reviewed last lecture? I missed it. The link's never uploaded. So the link is up now. You can go watch that old lecture if you want to. We talked more about logarithms. And can we work through the examples of how questions look on the exam rather than from WebAssign? Sure, yeah, although they're fairly simple. I can try to craft a few questions of the style of the exam. Before we get to that though, I do want to talk about applications. There are some special exponential functions that are used in applications a lot. Yes, we will do some reviewing. So, applications. In nature, many things can be modeled by exponential functions. If you have a conflict with the exam, yeah, I'll need you to send me an email or a Canvas message explaining the conflict, and we'll figure out some way to work around it. So the simplest example of an application, a setting where an exponential function shows up in nature, is if you think about how bacteria divide, right? Or how any single cell organism reproduces. That individual cell splits into 2 cells, and then each of those 2 cells split into 2 cells, and then each of those 2 cells, or each of those 4 cells split into 2 cells, can be modeled by. Many things can be modeled by exponential functions. So think about bacteria growth. You've got one bacteria, and he splits into 2. Or some other single cell thing. And then each of those split into 2. And then each of those split into 2. And so on. This is exponential growth. You've got one thing at this level, two things at this level, four things at this level, 8 things at this level. What's going on here is that we're doubling. We have 2 to the x things at the xth level. Modeled, yeah. And bacteria aren't the only things that divide this way, right? There's lots and lots of things where the next generation comes from each person in the previous generation multiplying so many times. This behavior, this repeated doubling, is best described by what's called a doubling time model. If some population doubles every a units of time, and initially has, say, C things, people, objects, then T units of time later the population will be, I think your textbook uses the symbol N. Let me know, be good. N of T will be C times 2 to the T over A. So questions about the test, detailed questions about the test, please Canvas message or email. Those are not class time questions. Let's keep the rest of those in the appropriate venue. Here, the 2 to the T over A, just like 2 to the X here, every time the exponent goes up by 1, you multiply by another factor of 2. So every time T goes up by A units, this exponent will go up by 1, which means we'll have another factor of 2. N of 0 here would be C times 2 to the 0 over A, which is C times 2 to the 0, which is C. So that's why we say C is the initial population, because 0 units of time after we started counting, C is the output from this function. Later, the word after time here, later, yeah. Another important model that we use a lot, I'll give a second since folks are clearly still writing. Another thing that happens a lot in nature is rather than doubling every so often, you might have a quantity that cuts in half every so often. The classic example here is half-life. If you talk about radioactive decay, you take a heavy version of a regular element like carbon, but with an extra neutron or two, will want to give off energy in the form of electromagnetic radiation. And as it does that, it actually loses mass. It loses material. One of the ways we talk about how long a radioactive substance will stay radioactive is in terms of this other model called half-life. And this is where the video game series gets its name. If you have any quantity, so some amount of stuff, which decays by half every A units of time, and initially has mass or size, call it quantity C, then T units of time later, that quantity will measure I'm not sure what the notation is that your book uses. I'll use just call it n of t again. This will be c times 1/2 to the t over a. And it's the same basic concept. Every time t goes up by a units, this exponent goes up by 1. So you multiply by another factor of 1/2. I want to introduce one other formula here, and then we'll look at some specific problems. The new homework that I'm opening up this week is very short. So 2 things are opening today. One of them is the quiz, the study guide for exam 3. And the other one is a short homework that focuses just on these application problems. So the last kind of model, exponential model here, is what your book calls relative growth rates. And this can be applied to literally anything. So if, I say again, some quantity is said to grow or decay with the relative rate r, then and initially measures at c units, then its growth or decay can be modeled by the function, I'll call this fella f of t. This is c times e to the rt. So these are your kind of 3 formulas. And if you took college algebra here at Santa Fe, you probably recognize all 3 of them. In college algebra, they call this continuous growth rate. Here, they call it relative growth rate. It's just a difference in the language the author of the textbook chose. You may remember me saying that the exponential function e to the x is special because its rate of change is equal to its height at any given point. The more complicated exponential that we have here, e to the rt, its rate of change is equal to its height times r. And that's where the term relative growth rate comes from, because the rate of growth relative to the overall size of the thing is r times the overall size of the thing. So if you're in a situation where you can only say how fast something is growing compared to where it is right now, then this guy is useful. If you're in a situation where the thing you're measuring gets chopped in half every so many units of time, then you're going to use the half-life model. And if you're in a situation where the thing you're measuring doubles every so often, then you will use the doubling time model. So I'll come back here, give you guys a minute to write and catch up, and then we're going to look at a problem for each of these. After that, I'm happy to do whatever you guys want. We can look at exam style questions, old questions from homework, whatever you like. So I'll give just a few seconds for everybody to write what they want to write. Okie dokie. So first, let's look at a doubling time problem. Squirrels, like rabbits, love to make more squirrels. That's kind of their only hobby. So maybe the population of squirrels let's make it fun. Let's call it Northside Park. Is counted in 2010 to be 300. And researchers discover that the population doubles every, let's say, 4 years. I'd like to do 3 things. Find a function which gives the population t years after 2010 tell me how many squirrels are there in this year, 2020, and maybe tell me when will the population, or when will there be 1,000 squirrels at Northside Park? Okay. And certainly problems very much like this have shown up on my exams. A variation of this problem has shown up on 2 of my last 4 exams from this portion of the class. So, what do we do?
Well, first we plug in all the variables that we have from the problem.
What do we plug them into?
The doubling time equation.
Good. Yeah, very good. So we got to figure out what kind of model we're going to use. And it's the case that we were told the population doubles every so often. So yeah, this is definitely a doubling time thing. So the best model to use here would be the doubling time model. Which is this. Now, I know that t is my variable. That's why we write the left-hand side like this, n of t, to emphasize that it is a number dependent on the variable t. But c and a are constants. What is the value of A?
4.
Good. A is the time to double. It's the doubling time. We double every 4 years. So A here would be 4. And what is C?
The initial population, so 300.
Good. Very good. So the number of squirrels at Northside Park T years after 2010 is 300 times 2 raised to the T over 4. And that's part A done. In part B, we want to know how many squirrels should there be in 2020? How would we figure that out?
Would we subtract 2020 minus 2010 to get T?
Good. Yeah, I'm going to plug some T value into this function. Remember, this function is the population. This is the number of squirrels. T years after 2010. So in 2020, T is equal to 10 because 2020 is 10 years later. 10 years after 2010. So the population of squirrels in 2020 will be my function evaluated at 10, which is 300 times 2 to the 10 over 4. And this is not a super nice number. For these sort of problems, you will often need a calculator at some point. This is 300. We can clean up 10 over 4 a little bit. If you divide top and bottom by 2, that's the same as, oops, sorry, my pen is dying, 5 halves. And then I can use a calculator or Desmos or whatever you would like to evaluate 300 times 2 raised to the 5 halves. And I get that this is about 1,697. Any questions on parts A and B? When you go plugging these sort of things into your calculator, there are a few things that you need to keep in mind. It's only the 2 which is being raised to the power 5 halves. Make sure you don't raise the 300 to that power also. And when you go to raise 2 to the 5 halves, you may need to put this exponent in parentheses, depending on the type of calculator you're using. I know that some calculators allow you to kind of shift up and stay in the exponent, but if you're using the calculator that this class calls for, and the only calculator that's permitted on the exam, you will need to put your exponent in parens. Yeah, T is the number of years after we started counting. So here in this setup, in 2010, they counted the number of squirrels to be 300. So 2010 corresponds to the year T equals 0, or the variable T, the value of the variable T equals 0. Okay. I'm going to switch colors here because that pen keeps dying on me. In part C, we want to know when will there be exactly 1,000 squirrels?
Okay, so for this one, I think, do you plug in 1,000 on the other side of the equation and then you find T?
Very good. right? So the thing I'm looking for here is a t value. I want to know when is something happening. That's going to be a time. It's going to be a number of years. This function tells me how many squirrels there are after t years. So I set this apparatus equal to 1,000. And since n of t is 300 times 2 to the t over 4, that means I'm solving 300 times 2 to the t over 4 equals 1,000. And this is an exponential equation. This is the type of equation that we were learning how to solve last week. So who can help me out with the first few steps here? Where would I get started if I want to solve this equation for the variable t, which is trapped in the exponent here? Good. First,
Divide by 300.
Isolate the exponential, and I'll do that by dividing both sides by 300. So that will give me 2 to the t over 4 equals 1,000 divided by 300. Now we can clean this up. That's the same as 10 divided by 3. So this is the same as saying 2 to the t over 4 is equal to 10/3. We'll just divide top and bottom by 100. What's my next step look like if I want to solve for t going from here? Good, we're going to need to take some sort of logarithm. We could use the base 2 logarithm if we wanted. We could use the base 10 logarithm if we wanted. But most of the time we just use the natural log. It doesn't matter, it's up to you. If you prefer using one logarithm or another, you're welcome to. But I'm going to take the natural log of both sides. And that will give me the natural log of 2 to the t over 4 equals the natural log of 10 over 3. All right, now what?
Use the properties now of the logs, and you put the exponent of t over 4 in front of the ln.
Very good. So I can bring this power down front. And I get this. And my goal, remember, is to solve for t. This is now easy to solve for t. 4 is a constant, natural log of 2 is a constant. So this is just t times some constant divided by another constant equals a third constant. Yeah, so I'll multiply both sides by 4, get rid of the 4. And then I'll divide both sides by the natural log of 2. And I get t as 4 times the natural log of 10/3 divided by the natural log of 2. Okay. Quick question. Is this the same as saying t equals 4 natural log 10/3 minus natural log 2? The answer here is no.
No, because the 4 is on the numerator there, and it'd be applied in the whole like division equation, other than you'd only be
Even with
applying
this,
the
it's
ln on
not
the other
true.
side.
So even if I make the 4 go to both, it's not true. right? And it's not because of the base. It's not because this is an ln rather than some other log. It's because the division here is going on the outside. So remember, the rule we have that works is that any log of a ratio inside can be written as a difference like this, but that's not the same as saying this. This one is good. This one is correct. This one is very much not good. Yeah, the division has to be going on inside. If I wanted to, I could expand this guy as ln10 minus ln3, as long as I remember to give the 4 to both. But this log divided by this log, there's nothing we can do there. Okay. So if I want to compute this number, the only move I have from here is to feed it to a calculator. I'll go ahead and do that just to give us an estimate here. We want 4 times the natural log of 10/3, all divided by the natural log of 2, which is about 6.9 years. So in what year will there be 1,000 squirrels? Well, 6.9 years after 2010, right?
Yep.
So towards the end of 2016, the population will reach 1,000.
Would you want us to round for that? Like, would you want us to write 7 years, or you want us to write like towards the end of 2016?
On exam questions, I will do 2 things. I'll ask you for the exact value in terms of logarithms, and then I may ask you for an approximate value. And if I ask you for an approximate value, I'll tell you exactly where to round. I'll say round to the third or first or second decimal.
Heard.
Okay. Any questions on this fella? Because 2016 is 6 years after 2010. So we know that 6.9 years later is when we will get this population up to 1,000. And that's 6.9 years after when we started counting, which was 2010. Okay, I see. All right, let's try a half-life problem. What is the half-life of carbon-14? 5,700 years. Okay. So the half-life of carbon-14 is 5,700 years. How long will it take a 2 kilogram sample of carbon-14 to decay to 1.15 kilograms? There's a bunch of different ways to sort of think about these. Maybe I dig something up out of the ground and I measure that it has 1.15 kilograms of carbon-14. I know that it originally contained 2 kilograms of carbon-14. I could ask, how old is the object? And this is actually how radiocarbon dating works. But let's see if we can just answer this question. We need to begin with the half-life formula. Here, the amount of stuff we have t years later is c times 1/2 to the t over a. A is the amount of time it takes for half the stuff to go away, and c is the initial quantity. So what should I plug in for the constants c and a here? What would a be? Good, see here, the initial amount is 2 kilograms, or just 2 if you want to ignore the units. And what is a? Well, a is the amount of time it takes for half of the stuff to go away.
5,700?
Yeah, which is the half-life, is 5,700. So my model, my function that I use to model the physical situation is 2 times 1/2 to the t over 5,700. This is true, by the way, right? You take a lump of carbon-14, let it sit for 5,700 years, it will weigh half as much because it actually decays. All right. How do I take this model and use it to answer the question? Very good. Yeah, this is the amount of carbon-14 I have after t years. If I started with 2 kilograms, I want to know how long it's going to take to get down to 1.15 kilograms. So I set this thing equal to 1.15 and solve for t. And that means 2 times 1/2 to the t over 5,700 would be equal to 1.15. And the process for solving this is very similar to the process we used to solve the last exponential equation. First, we have to isolate the exponential term, which is this guy. Yep, so we do that by dividing by 2. And I'll just write that as 1.15 divided by 2. There's no harm in that. And then I would take logs. And the most natural thing to do, sorry for the pun, is to take the ln of both sides, the natural log. So there's the natural log of the left, and it's equal to the natural log of the right. Now, just like in the previous example, the power which contains my variable can be brought down in front. So I get t over 5,700 times the natural log of 1/2, is equal to the natural log of 1.15 over 2. And then I need to multiply both sides by 5,700 and divide both sides by the natural log of 1/2. So this is the same as saying t times the natural log of 1/2 is equal to 5,700 times the natural log of 1.15 over 2. And then finally, I'll divide both sides by this constant. And as long as you do things carefully, don't go canceling things that don't cancel, like never try to cancel the ln's, those don't cancel. Don't try to cancel the inside of the logarithms, that doesn't work. You gotta just leave everything as it is. We get this. And like I said, I can't cancel the 1/2 inside this log with the 1/2 inside this log because they're both trapped inside the logs. So you just got to deal with it like this. But you feed this to your calculator carefully using appropriate parentheses. And you get the result. Take about 4,500 years. We'll say times 0.7 years. You could expand the natural log in the top. You could actually expand both of them, this one and this one. But because that's going to introduce some subtraction up here and some subtraction down here, there won't be any cancellation because the natural log of 2 that's going to come out from that won't be a factor of the top or of the bottom. So for my money, it's best to just leave it like this. That would be my recommendation, yes. You could expand it, but it's only going to make the calculation more troublesome, not less. You should always do a common sense check at the end of these problems. So for example, I know that the half-life here is 5,700 years. If I found that to get down to 1.15 kilograms, it was going to take 10,000 years, I would know something's wrong. Because 10,000 is way more than 5,700. It's almost double that. But I'm not trying to find out when the thing is decayed by more than half. Decaying by half would be 1 kilogram. So if I got an answer here that was larger than the half-life, I would know I made a mistake. Similarly for that squirrel problem. Since in 2020, there was more than 1,000 squirrels. If I got an answer bigger than 10 for the part C, I would know I made a mistake. So yeah, my advice when it comes to the calculations, don't try to get fancy with the logarithms. No need to get fancier than the problem calls for. It only introduces places to make mistakes. And then at the end of the problem, do a common sense check. You know, if you've got some points that you know, like after 5,700 years, there would be 1 kilogram because that's half of 2. You know your answer here should be less than 5,700, and it is. Okay, that's a good common sense check that can get you out of some spots. Any questions on what we did here? All right. And for my last example, I'll grab a problem from your current homework. The homework that opens today. take a look at one of these guys. One of the relative rate. All right. So here we're told that the population of foxes in a certain region has a relative growth rate of 9%. And the population in 2013 was 19,000. We want to find a function that tells me how many foxes there are t years later. So I'll write these basic facts down and then switch back to the .cam. There are 19,000 foxes. We want to do a few things. First, find a model. Second, estimate the population in 2019. Third, say when the population will reach 25,000. And fourth, sketch a graph. All right, I think that's everything here. Yeah, okay. So these are the basics condensed. Since I'm told that this is a relative growth rate, I know I need to use that formula. So for part A, I'll begin with the formula. I think I called it f of t. You can use whatever label you want. Is some constant times e to the rt. R is my relative growth rate, 9%, and I have to write that as a decimal. Remember, percent means out of 100. So that's 9 over 100, or if you like it as a decimal, 0.09. C, my initial population, they told me in 2013 the population is 19,000, and they want the function to tell them how many there are after 2013. So we don't have to do any funny business here. C is just 19,000. So my function, which models the population t years later, is 19,000 times e to the 0.09 t. That's our model. And if I want to know how many foxes there are 10 years later, I would plug in t equals 10. If I want to know how many foxes there are 50 years later, I would plug in t equals 50. In part B, I want to know how many foxes will there be in 2019. Well, 2019 is 6 years after 2013. So we plug t equals 6. F of 6 should be the population in 2019. That's 19,000 times e to the 0.09 times 6. And again, here we're going to need to employ a calculator. E is a nasty number to work with by hand if you want 21 decimals. So I ask my calculator, what is 19,000 times e raised to the 0.09 times 6? It's 32,604. So there will be 32,604 foxes in 2019. Part C, you can get a feel. These all kind of ask the same sort of things. When will the population reach 25,000? We need to solve f of t equals 25,000, which is the same as saying 19,000 times e to the 0.09 t equals 25,000. And based on the answer we got in part A, I expect this t value to be less than 6, right? Because 6 years later, the population's at 32,000. And since this population is only growing, the year where it's going to be 25,000 has to be between 2013, when the population is 19,000, and 2019, when the population is 32,000. We solve this the same way we solve all these other guys. Isolate the exponential term. Uh, 25,000 over 19,000 is the same as 25 over 19. So I'll write it like that because it makes life much nicer. And then I'll take the natural log on both sides. Now on the left-hand side, I have a natural log of an exponential. What does this simplify to? Mm,
0.09 t.
Yeah, 0.09 t. So the natural log of e on its own is 1, but the natural log of e raised to some stuff is always going to be that stuff. So let me show you how this goes. You can handle this the same way we've been handling all the others. Bring the power down and then deal with the constants. So here's the power, and then you would be left with the natural log of e here. And on the right-hand side, you still have your natural log of 25 over 19. And the natural log of e is 1. So we'll have 0.09 t equals the natural log of 25 over 19, because this piece is just 1, and this times 1 is just this. And now finally we can divide by the 0.09. Which we can approximate using a calculator. So this is the natural log of 25 divided by 19, all divided by 0.09. You want to be careful with your parentheses, of course. We get 3.04. And that's close to 3. We'll just call that 3 years. So it will take 3 years for the population to reach 25,000. In other words, the fox population reaches 25,000 in what year?
2016.
Good. 3 years after we started counting. We started counting in 2013, so that's 2016. Okay. So I think this is probably enough practice with these sort of things. There are some other problems in this homework that will require you to think a little bit more carefully, but they all follow this basic sort of pattern, where you come up with a model and then you use the model to answer some questions. The most crucial step here is coming up with the model. Are there any questions about how we came up with any of the functions that we used to model these real world things? Any questions about the algebra we used to solve any of the corresponding equations? Or how we maybe could or maybe could not simplify any of these things? All right, if not, then I just want to draw your attention to one or two more specific things within this homework set. Let's see. 25 hours. 10 years from now, graph, all the shit, graph. There are one or two problems where you're asked to do something a little bit neat. Here you have a doubling time problem, and then they ask you to find a way of writing it like this. N0 here is just a constant. I've been using C in place of the constant N0. How could you take something like this and rewrite it as something like this? That's an interesting thing to try and sort out. I'd like to try one problem along those lines. Everything else here, very self-explanatory. Yeah. All right. So we're going to do one more little example, and then we can do whatever you guys like with the rest of the time. So suppose a population is initially, I'll say 500, let's just keep the numbers nice and tight, and doubles every 7 years. Can we find the relative growth rate and write the model both ways, i.e. as doubling time and relative growth? I should say period, right? Not question mark, just do it. We can do it. How do we do it? Where could I begin here? Which model is easier to write down given the information they provided? Yeah, the doubling time one. They gave me the initial population and they gave me the doubling time. So from the doubling time perspective, This population follows the formula C times 2 to the T over A, where C is 500 and A is 7. So N of T is 500 times 2 raised to the T over 7. I want to know, how do I write this as C times e to the RT? There is more than one way to answer this question. Let me call this one N of T, and the other one I'll call F of T. That way we have different labels for each, and we can play with them. Do I know what C would have to be here? It would again have to be 500. Yeah. So N of 0, in other words, what we want to do is such that N of T is equal to F of T, right? These things are both measuring the same thing. They're both measuring the same population. So they should always be equal to each other. In particular, when you plug in 0, they should be equal to each other. If you plug in 0 on the N of T guy, you get 500 times 2 to the 0, which is just 500. And if you plug in 0 here, you get C times e to the 0, which is just C. So F of T is going to be 500 times e to the RT. And we want, remember, F of T and N of T to be always equal. So I could say, now N of T is equal to F of T means the same thing as 500 times 2 to the T over 7 equals 500 times e to the RT. What am I really trying to solve for here? What piece of information do I not know, which if I did know, I would be able to write down the answer? It's not t in this case, it's something else. Remember, t is like my variable. I'm trying to find a way to write my other function like this. So the t should just be t in both of these expressions. But the piece that I don't have down here, I just found C. I know C would be 500. Well, E is just a number, right? It's like 2.71828. It's a constant. Yeah, the thing I don't know is R. And I said, can we find the relative growth rate? So the thing I'm trying to solve for here is R. I can divide both sides by 500. And I get 2 to the T over 7 equals E to the R times T. And then from here, there's more than one way to skin this cat, but I think the most natural thing to do is to take logs. So ln of 2 to the T over 7 is equal to the ln of e to the RT. The left-hand side simplifies to t over 7 times the natural log of 2, and the right-hand side simplifies to RT. Yeah, good. This is, I'm going to write this as t times 1/7 natural log of 2 equals t times r. If you then divide both sides by t, then you'll get 1/7 times the natural log of 2 is equal to r. So this is our guy. In other words, the relative growth rate is r equals ln2 over 7, which we can, again, approximate using a calculator. As 0.9902. 0.09902. Or about, what is that as a percentage? That's about 9.902% per year. Nifty, right? So you can go from one form to another. You can go from doubling time to relative growth rate. You could similarly go from relative growth rate to doubling time. Or half-life to doubling time. Or half-life to growth rate. All of these are manageable. All right. So that is everything I wanted to show you guys and everything that you guys need to knock out this last very small homework between now and the test. The rest of the class, I'm happy to do whatever you guys want. So are there any problems bothering you? Anything that's been just driving you nuts in this homework lately, or any of the other homeworks since exam 2? Anything to do with exponentials and logs that you guys would like to talk about in more detail?
I have a quick question.
Yeah.
Or for the test, is there gonna be compound interest questions in it?
Fuck it, I'll just tell you, nope. Nah, no compound interest. I know you guys hate that shit. It's just formula stuff. I don't think anybody really at this level cares about it enough to investigate the deeper meanings. So no, I'm not gonna hit you with any compound interest.
Amazing, thank you.
How we'd write problems on the exam versus in WebAssign, is anybody could study or have an idea of what multiple choice questions will be? Well, so I can't tell you what the multiple choice questions will be. That certainly wouldn't be right of me to do. Yeah, sure, why not? So here's an example true false question. I'll give you a few of them. write this a little bigger. All right. So here we go. You got some true, false. What's up with that first guy? Is he true or is he false?
He's true.
He is true. What about the second guy?
I'm like leaning towards the, I don't know.
He's
I feel like
also
he's
true.
false.
If you
Oh,
factor the inside is x minus 1 times x plus 1. So that is indeed equal to the natural log of x minus 1 plus the natural log of x plus 1. This multiplication inside the log turning into addition outside the log. So yeah, the first two are true. What about the third guy? Third is false. Remember, log of x over y is, as regardless of base, log x minus log y, but log of x over log of y is not equal to that. Different animals, right? So division inside versus division outside, they're very, very different. What about the bottom one? What about the fourth one? True or false? Good, this is false. And there's a couple ways you could see it. First, you know that this one's true. And is this the same as this? Nah. Now, what am I trying to do here? I'm trying to catch you out. I'm trying to see if you'll go, okay, well, this is the ln of x squared minus 1 squared, and can I bring that 2 down front? Is this kosher? Is the light blue here kosher? Nah, why not?
because that looks like x minus 1 is squared.
Right. What is, so this is not equal to that. What is equal to 2 times the natural log of x minus 1 would be the natural log of x minus 1 all squared. And since these are not the same, this is not equal to this. Yeah, good. Okay. I could ask you to, select the correct graph. Of natural log 1 plus x, or even to draw the graph of the natural log of 1 plus x. How would you do that?
You just like plug in a bunch of x values where the x is, where the ln, or no?
I wouldn't. No. No, I would think this as a transformation.
Wait. Oh wait, does that say 11x or 1 plus x?
1 plus x.
Oh, I thought it said 11x. Sorry.
No, that's okay. Okay. So this is a transformation of regular old ln x. What do I need to do to the regular ln x graph to get this graph? Good, one shift left. What does the regular ln x graph look like? I know that's not an easy thing to answer here via Zoom. It has a vertical asymptote at x equals 0, which it approaches only from the right, and then looks like this. What is this x-intercept here on the graph of ln x? Not the transformed one, but the original one. Good, 1, 0. If I come all the way out here to x equals e, what's the point on the original graph associated with x equals e? he would be e comma 1, because the natural log of e is 1. So if we transform this bad boy by shifting left 1 unit, my new VA, my new vertical asymptote will be the line x equals -1. I will approach it from the right. Instead of going through 1, 0, I will go through 0, 0. If I tell you this point has y value 1, what is the x value? In other words, where does this point get moved to when I shift everything to the left 1 unit?
Just moves one left, right?
Yep. Yeah. So I'm just moving this point
Yeah.
1 unit to the left. So what's the new x value?
Is it like? Yeah.
Not quite. E plus 1 is a good guess. You can always
That
check
was a
this
good
by,
guess.
yeah, e minus 1. You can check it
E
by
minus
plugging
1.
in here, right? If I plug in e minus 1 for x, then I get 1 plus e minus 1, which is just the natural log of e. So this is indeed e minus 1. Similar questions I could ask you about exponentials, right? How do you transform the base, the regular exponential into something like shift left, up 1, that sort of stuff. I could ask you to find domains. Domain of maybe the natural log of 4 minus x squared. How would you find that?
That's
Yeah,
negative
correct,
infinity
Elliot.
to
Which should
positive
be right,
infinity.
that would have been e plus 1. What was the, Ronald, did you just answer the domain here? What do we do?
I said at first I said negative infinity to positive infinity, but I'm not sure if there's a vertical asymptote.
No, unfortunately, it's more complicated than that. What do
Yeah.
all logarithms require of their interiors? Remember, we learned a new red flag. What needs to be true about the inside of a logarithm?
Oh, the stuff has to be positive on the inside. There can't be any negatives.
Good. So I need to solve the inequality 4 minus x squared is greater than 0. And this is an inequality like I could have put on the last exam, right? It's a nonlinear inequality. So how do we solve that? I wouldn't go subtracting here. Remember, nonlinear inequalities, we factor both sides. We pull everything to one side, then we factor. So this is 2 minus x times 2 plus x is greater than 0. Then we plot the special numbers on a number line. So my special numbers are -2 and +2. Then we test a point from each region. If I plug in x equals 0 here, I get +4. So I can test a point from the middle region and then use my multiplicity trick to say we will change sign here, we will change sign here. So the domain is the open interval from -2 to 2. And these are the sort of questions I'll be asking you on the test. They'll largely have to do with either graphing, solving an equation, expanding or contracting logarithms, or solving an application problem of the type that we looked at today. I put some real time into putting together your study guide. The study guide should be very much representative of the problems you'll find on the exam. So if you put some love into that study guide, you will do okay on this test. This is not a bad test as long as you've taken the time to internalize those logarithm rules. Remember, there's a lot of ways to mess these up, right? There's a lot of ways to think about log rules incorrectly. So I would first focus on those and make sure you're comfortable with them. The questions from the packet that I sent out, the logarithms properties packet that we were playing with for the last couple of weeks, if you work through all of those, I would say you can be reasonably confident you will not miss any of these type questions. For the rest of it, make sure you've done the homework, make sure you're comfy with graphs, do the study guide, make sure you're comfy with domain rules, and you'll be okay. Right? If you do have any particular questions, you can come see me in office hours, or as always, you can send me an email or a Canvas message, and I'd be happy to talk to you guys there. We don't have a class this Wednesday, but I will be doing normal office hours and stuff through this week. So if you wanted to come see me on Wednesday, or if you want to come see me around Thursday, anything like that, you're more than welcome to do so. Any last minute questions before we depart?
Yeah, okay, one last question and that's it. One thing that keeps taking me out, like in the homework, like the old homework, was the range. Like whenever I was graphing these, because like whenever it would be like the transformation would be, for example, like to move it up or down, like the range wouldn't be the exact number that's in the formula. Like it would always be like 1 down or 1. You get me? Like you get what I'm saying?
Yeah, well, so in order to get the range, you need a good picture of the graph. That's the
Right.
big thing. So these logarithm functions, they all have range, all real numbers. So you move it up or down, the range won't change. But exponentials, as you move them up or down, the range does change. So for example, if you look at like regular old e to the x, his range is 0 to infinity.
Right.
So if I drag this down, if I look at e to the x minus 1 like that, that's going to shift the whole graph down 1 unit. So my new range would be -1 to infinity.
And then the horizontal asymptote would also be -1.
Yep. Yeah, the HA would move.
All right.
Here the HA was y equals 0. Here the HA would move down to y equals -1.
Perfect.
Alrighty, guys, I gotta get running. I hope you guys have a lovely rest of your day. And if you want to talk more, just come see me in my office hour, okay? And any questions you had about the exam, Gabriel, I'm sorry I didn't have time to answer that during class today. You can come see me in the office hour, or you can email me the question. I'll be happy to deal with it there. All right, take care, guys. I will see you either in office hours or next Wednesday.